Hello everyone, this is Space Cafe Podcast, and I am Marcus. Intellectual frustration gives me strange pleasure. This is what I call the reshaping of my knowledge in the grand scheme of being, and how I keep reminding myself how small I am and how little I know. Take, for example, the night sky. If you look up with your bare eyes, and if you had the time to count, you might be able to count 5,000 stars and planets, roughly. So how much is that compared to the objects in our home galaxy, the Milky Way? Well, as there are about 100 to 400 billion stars, the number that we are able to discern with our naked eyes is quite small. About 0.000000125% are visible to our feeble human eyes. But we have barely started. So there are estimates that there are 100 billion to 200 billion galaxies in the observable universe. So let's do the math again. Let's take the original number we just calculated and divide it by 100 billion to 200 billion. That produces a number with 17 zeros below my frozen mind. But let's take this even further. Some estimates suggest that there might be up to 2 trillion galaxies in the entire universe, which of course we will never see, but just for the fun of mutual intellectual frustration, let's do the math one more time. Let's take the original number we just calculated that brings the objects that are visible to the naked human eye in relation to the Milky Way. So, let's take that number and divide it by 2 trillion. That produces a number with 19 zeros below zero. And that is just the stars, my friends. No planets, no moons, and whatsoever. But alas, there is hope. There is always hope in Space Cafe podcast land, because today we're bringing light into the dark with our special guest, Dr. Knicole Colon, an astrophysicist from NASA's Goddard Space Flight Center and an expert in the exploration of exoplanets.
There's so much out there in the universe waiting to be explored. So just try to fathom that. It's a way to remember you're not alone, because the universe is very big, but in a good way.
Knicole delves into the unknown realms of the universe, seeking out the tantalizing possibility of life on distant worlds. She's our cosmic cartographer, plotting a course through the universe's mysteries. In our enlightening conversation, we're touching upon the thrilling search for exoplanets, the rigorous science behind their discovery, the potential for life beyond Earth, the rising interest in interplanetary travel, and the profound implications of space colonization. Knicole will also share her personal love for the Orion constellation, discuss the necessity of collaboration in space exploration, and leave us with an inspirational message that underlines the vastness of the universe and the comforting idea that we're not alone in it. So fasten your seatbelts, fellow explorers. We're about to embark on an interstellar journey, delving into the heart of the universe's greatest mysteries. Off we go. Enjoy. What's your panel about?
So our panel, we had a panel about the James Webb Space Telescope that's led by NASA's agency, but also the European Space Agency and the Canadian Space Agency. So we were firstly revealing a brand new image that nobody had ever seen before. So that was super exciting from the telescope. It was of a dying star. And so it just really represented the evolution of the universe, but in the sense of these dying stars shed all this material that eventually turns into new stars and new planets and
And you.
Potentially us. Yeah, exactly. So that was a beautiful picture that came out. First time ever. Nobody had seen it before.
Wow. How long is the dying process of a star? How long does that take?
Oh, it actually depends on how big the star is. But it's still much longer than a human lifetime. We're talking millions to billions of years, depending on the type of star.
So the dying process lasts a couple of million or billion years.
Yeah. Yeah, it's a long time.
Our sun is 4.5 billion years old, right?
Yeah, it's like middle age.
Okay, so it's halfway.
Yeah.
Okay.
So it's still got a ways to go before it starts to evolve, and it'll actually get a lot bigger than it is now. And so we think what will happen is that as our sun gets bigger, all the planets will kind of move outward along, it kind of scales.
Like run away?
Yeah, like we're running away from the star that's growing, essentially. And we're, expecting that to happen. But then at some point, our sun will shed outer layers of gas, and that process, even though shedding sounds gentle, it's probably going to destroy some of the planets in the process just because it's extra material. Probably. Yeah.
So let's go through this. I guess we're not going to be around then.
Yes.
But so the sun will grow, will extend its diameter massively.
Yes.
Why is that?
Yeah, it's a process. I mean, so all stars are really just really hot balls of gas, but they have a bunch of elements in them and they have fusion processes. And at some point, the fusion will essentially eat up all the hydrogen. And so
Fuel.
Yeah, you're eating up the fuel. So that way, when you kind of run out of fuel, then other things start getting fused. And so that causes expansion of the star because it's just a different chemical process and different energy that's going on, and it bloats the star.
Sure.
And at some point, it kicks off like enough energy that it starts kicking out its outer layers of gas because it's just like layers and layers. It's like almost like a shell of gas, but many layers, like an onion.
Am I understanding a star right when I say a star always wants to explode outward, but it can't because of gravity? And this is why the stars are stable?
Yeah. Normally, it is a very stable process once it hits what we call the main sequence. It's just like the main lifetime of the star. So when stars first form, it is very chaotic and energetic. But at some point, they stabilize, and you're just fusing hydrogen into helium and just moving along for billions of years in a happy, steady state. And then, at some point, that you use up the fuel that you started with, and then these new processes begin, and then the stars just keep moving on to the next phase. And then once they kick off and effectively die, they could die in different ways. And so what will happen to our star is it will shed all its outer layers, and what will be left is a very tiny remnant in the middle called a white dwarf. And it's extremely hot, extremely dense, but it's not necessarily a star you want to live around either.
Because would I see it? Does it emit light?
Yeah, it's very bright. I mean, it's a white dwarf for a reason. They appear white, basically, or they would appear white to our human eyes. But they appear white because they're so hot. If you imagine, a flame, you see stars kind of match those colors. Like the hottest flames are blue, actually, and then it transforms to white as the hottest of the hottest flame. And that's the same thing with stars. The hotter stars are blue, and then white is the absolute hottest you can go. And
how hot is that?
In
Celsius.
In Celsius. Oh, gosh. That's a good question. Hotter than I can fathom. Yeah, our sun, I can tell you in Kelvin.
Sure.
It's about...
Let's do Kelvin. Yeah. And there's calculators out there.
That's
Google
right.
Kelvin to Celsius.
Absolutely. That's honestly how I do it, too. But our sun, it's around 5,800 Kelvin. And if you take a white dwarf star, it's going to be twice as hot as that, in like the tens of thousands of Kelvin. And so, yeah, if you translate that to Celsius or Fahrenheit, it's probably, millions of degrees.
Wow. So what is it made of? The white dwarf?
Oh, the white dwarf. Oh, yeah, it's basically like leftover ultra dense neutrinos, like these super heavy elements that are just hard to fathom. They are, some of these stars are so dense, there's analogies where it's like, fitting the mass of a sun, let's say a giant ball of gas and dust, but it's very massive, fitting that into the size of a city.
Huh.
Like the density scales, it's incredible. Yeah.
But it's not dense enough to become a black hole.
It's not, yeah, because it didn't start with enough mass. Okay. So, so our sun is, I mentioned it's a middle-aged star, but it's also kind of like a middle-weight star. So it's just kind of a standard star. But if you have something that is more massive, like even just a few times more massive
like
than the sun.
Beetlejuice?
Yeah, then that could erupt, essentially. Like its processes over time, its fusion and all that, it becomes so unstable, like it won't just shed layers, it will explode them away. And so it could go supernova, and it's this really energetic, violent, bright event, which is really incredible to see. But what's often left at the end of that is a black hole or another type of star, a neutron star, so another ultra-dense star. But they're all very tiny, compact objects usually. Like they're so much smaller than the stars that started. It's almost like magic. It's physics, but it's incredible to think about how these densities work and like just how heavy things can be when it's hard to describe it, right? But yeah, these things just end up in these amazing states of life that, there's these explosions and then there's nothing, like a black hole. It's something, but you can't see it. It's black.
Before becoming a black hole, would this very dense matter, what would that look like? Would it look like right here, like a table, just like a solid surface? Would it be able, of course it's not, this is very, maybe not super realistic to be able to touch something like this, but just for the sake of the argument, what could that surface look like?
Yeah, I think, it's interesting because it's all gas. We're walking through an atmosphere, we're breathing an atmosphere right now that's gas. We don't see it, right? But imagine, I guess, a gas so dense that, it hits you like a brick wall. So it's still not a solid.
Wow.
So
this I don't understand.
Yeah.
So how does that work?
It's just, it's like rearranging molecules, like within you to make you more dense. Like if you, I'm trying to think of a good analogy, if you imagine if you're in a swimming pool and, you feel like lightweight, even though you weigh a certain amount in reality, but in the pool you feel different, right? You feel like you're floating, but you technically weigh the same, like you are the same person. So in this case, and water's not a solid, right? It's a liquid. So again, not a gas, but it's still something solid. Like if you jump off a diving board into a pool and you belly flop, that hurts.
Exactly, that hurts.
So it's a liquid.
Water. Yeah, it's still liquid.
It's a liquid, but it hurts like a solid.
It feels like concrete.
Yeah. So it's the same concept, like where now instead of water, it's a gas.
Like the atmosphere when spacecraft.
Yeah, you're still hitting an atmosphere. Yeah, and it could
bounce off even.
Yeah, if you hit it at the right speed, or again, it's so dense, like all of those things combined. Or in this case, it's so dense. I think if you just walked into it, it would be the same concept where it hurts. Like you don't want a belly flop in the pool. You don't You don't want,
Or
your
white
shuttle, you want your shuttle to make it through the atmosphere and like survive, swimming through the gas, even though it's a gas, it's not liquid in the atmosphere, right? So it's like, it's a weird concept for sure, but
it's real.
But it's real. Yeah.
What is the biggest known star out there?
Oh gosh. I mean, so
Or how
we
big?
always, we always use our sun as kind of like a template, right? For everything, a scale. And, even though you can see the sun in the sky, it's a lot bigger than it looks, compared to how we see it from Earth. But the stars that are bigger than that, I mean, there are some like 30 times bigger. Off the top of my head, I couldn't tell you which one is the biggest, but there are many that are a lot bigger where the sun looks.
So our sun is not a big deal.
It's it's an average deal. Yeah. Yeah.
To me, it's fascinating how human knowledge is expanding over the centuries, because there was a time before Copernicus when we believed that we're at the center of the universe. And then we learned through Copernicus that it's the sun at the center. So the sun is the most important thing. And then at some point we learn, well, the sun is amongst many suns. It's just a solar system amongst many solar systems. And then we find out, solar system is part of a galaxy. Interesting. But the galaxy is part of a myriad of galaxies and galaxy clusters. So what's the point of all of this? I mean, like, do we even exist?
Yeah, it's mind-boggling, right? Exactly. Like we are, we have 8 major planets orbiting the sun, and then a bunch of comets, asteroids, small planets, including Pluto is a minor planet.
It is.
Yeah, it's a minor planet. It's not a major planet, but that's okay. But yeah, so we have all these things that orbit the sun, sure. But then, you're right, there are billions of stars that make up our Milky Way galaxy. So they all kind of orbit together around this massive center. And then you take that and you say, okay, now there are billions of galaxies out there in the universe that we know of. We're still looking. The James Webb Space Telescope is showing us there are more galaxies out there than we even realized. Yeah. And each of those has billions of stars. And, we're still finding planets in our own galaxy. We found over 5,000, but we're not done looking yet. And so even though we've only found 5,000 and there are billions of stars in our galaxy, we still extrapolate that, on average, when you look at any star, it's likely to have at least one planet. So another way to think about it, I mean, honestly, is, well, the reality is probably that planets outnumber stars, really. Because, I mean, if you look at our sun, again, we have 8 planets and there's one star. So if you just imagine the numbers, it's like trillions and
so you need
trillions.
to multiply the number of stars by 5 to whatever.
Billions times trillions. Yeah, and so if you take that and you imagine how, to put a pun, like how on earth could we be the only type of life out there, even ignoring intelligent life, could Earth have been the only planet that could sustain any type of life? That's obviously a big question that drives us. Are we alone, right?
Yeah. It's crazy.
It does drive us crazy because we want to know, but space is so big, it's hard to, get a quick answer. Yeah.
So now the obvious question, you're specializing in exoplanets. The obvious question, I'm not asking as to if we're alone, but is there another Earth-like planet out there? And can we see it already?
Yeah, well, so I mentioned we found over 5,000 planets so far around other stars. And they do range from all sizes, from some of them are Earth size, some of them go up to Jupiter size, like 10, 11, 12 times the size of Earth. And so we found a nice range of planets. But then the question is, okay, looking at the ones that are around the size of Earth, are there any that orbit stars like the sun, right? Do they have the same temperature as Earth? because, we think we need a planet with a similar temperature to have liquid water oceans, right?
Could it be Venus? And that
Exactly, because, we see Venus is an Earth twin in many ways, but it's not habitable. Yeah, it's totally inhospitable. And so, we can be tricked, right? Like, are the Earth-sized planets that we're finding, if, they're just a little too warm, a little too close to their stars, did they, evolve like Venus and form this deadly atmosphere that you cannot live in? Or could they have formed like Earth, right?
Has Venus perhaps undergone a human-like civilization with climate change destroying its atmosphere? And now we're seeing what we're headed towards as humans on Earth.
People have thought about this. I mean, I think it's hard to say without being able to go there. Like, we've sent some satellites to Venus, but they don't last very long through the atmosphere because it's that poisonous. So it's not like we can send landers easily like we do to Mars. And, they roam around and dig up dirt. Yeah. It's in Venus, they are very, very short-lived.
There were missions in the 70s or 80s, if I remember correct.
Yeah, there have been a few. And, we've had some pictures of, the surface of Venus, but it's very few and far between because it's so incredibly hard. So this is a priority, I think, as we're finding all these exoplanets. This is something that, astronomers are definitely pushing for. Like, we need to study Venus more as much as we can, however we can, because we need to know, could any other exoplanet be like Earth, or are most of them going to end up like Venus? If they're too warm, if they're just slightly too warm, right? Are we really in a Goldilocks zone?
Is there a chance that Venus underwent some sort of climate change situation, and maybe this is also where Earth is headed towards, irrespective of our human doings?
I mean, it's possible, because even Earth has undergone its own climate changes before humans were really around. So it's just a process. I mean, as the sun evolved, we talked about the process of forming a star is very chaotic in the beginning, and the stars emit like these giant flares and, activity that then hits the atmosphere. It's just massive doses of radiation, basically, right? And we still have solar flares that affect us. Sometimes we get GPS glitches, and it's because there was a solar flare that went off, And so imagine that, but more intense in, back in the day, we'll say millions, billions of years ago. But so imagine then Venus is closer to the sun than Earth. So it basically got more bombarded by that activity than Earth ever did. So, could Venus have survived that and then had a hospitable atmosphere for a short time? Or did it, start with a hospitable atmosphere, but then, the sun caused some climate change? I think that's still an open question. I mean, and that's something else we're looking at with Mars equally. Like, it's colder than Earth, it's further away, but it used to be warmer. And that's why we look for water there, because it used to be warmer, even though it's actually half the size of Earth, it's small. It's still a promising environment, for maybe it had some type of even bacterial, microbial life in the past that got killed once the sun kind of cooled down a little bit.
Would we see remnants still?
Yeah, I mean, we're looking all the time. That's one reason we send so many missions to Mars, because we can actually, it's relatively easy to go there. But we can literally dig through the dirt, and we're starting to work on things where we can do sample returns and pick up Martian dirt and try to measure properties and, look for any hint in the life. I mean, even if it's fossils or, the composition of the dirt, if it contains traces of genetic material, whatever that genetic material is, not human material, right? But anything that could be indicative of a carbon-based life form, we'll say, right? But it goes beyond that, because there's a lot of planets in our solar system, and a lot of them, like Jupiter, it's also a giant ball of gas. Like there's no life there. I mean, there's not really a solid surface. It's just.
Does life need a solid surface?
Well, that's a good question. Probably. Well, because we think life needs water and liquid water. And so I think it's less about having a solid surface than when you're in a planet like Jupiter. There's so many layers of gas and like clouds and material, if you will, that above a potentially rocky core, that the pressure from all that gas would kill you, basically, would kill anything. So it's really about like, there might be a solid surface underneath all those layers of clouds, but it's just not livable because the pressure is just too high for anything to survive. Unless, there's something we haven't thought of, science fiction, wise, some type of interesting life form that could survive in high pressures. I don't know. But the interesting thing is these planets have a lot of moons, and several of those moons have liquid oceans. They do, for a fact. And so...
Europa.
Yeah, exactly. Europa. Titan is another one that... Titan almost looks like a past Earth, where that there was a lot of haze and a denser atmosphere in the past when Earth was first formed. So we call it an Archean Earth model. And so... is Titan a good example of what Earth used to be like in the past? And we're actually planning missions to go to these moons, which is really exciting to see. Could there have been, or are there active signs of life there now? There might be, which is amazing.
So we got our solar system covered when it comes to trying to find out if there was life somewhere at some point. But from a statistical point of view, it makes more sense to go way beyond our solar system, because just to have a greater sample size. So, and this is where you come in with exoplanet research. So where is exoplanet research these days? How far are we?
Yeah, that's a great question, because with exoplanets, we kind of started off just counting. We're like, how many are there? How many can we find outside of the solar system? Like,
it's not that old that we know that exoplanets are out there. So I think when was the first exoplanet found?
Yeah, it hasn't been that long exactly. I mean, it was depends who you ask on what the definition of the first planet was, but it was in the 1990s. Essentially that. So just a few decades ago that we found the first planets outside the solar system, and we knew that it was the beginning of a literally new era in astrophysics, because we had
the iPhone moment for astrophysics.
Yeah.
Or ChatGPT moment.
Exactly. Where we're like, okay, now what do we do? Now we know there's planets out there. Let's A, see how many there are, and then B, what can we measure about them? What can we tell about their properties? And so now we're at the point where, again, we know of over 5,000, and we're still hunting for more every day. There are active planet hunters out there. NASA has the Transiting Exoplanet Survey Satellite called TESS, and it's actively hunting for planets all the time. So we're still looking for more, but of the ones we know of, we've been able to start doing deeper dives. Like, we can measure things like their sizes and masses. We are digging into their atmospheres now, too. And it's interesting that we're able to do this when so many of these planets are far away. Like, they're all in our galaxy, but it's not like sending a probe to Mars, a lander to Mars, even to Jupiter.
Light years away.
Yeah, sometimes hundreds of light years away, where it would take you, if you could travel at the speed of light, it would take hundreds of years to get there. So when we're studying these planets, what we can do is use telescopes like the Hubble Space Telescope, James Webb Space Telescope, and study that thin sliver of atmosphere around the surface of the planet. And in a way, it's simple, because all we're doing is measuring starlight from the star that the planet's orbiting. We're measuring the starlight that gets filtered by the atmosphere and then hits our telescope. So we basically are looking at starlight, But then we see where kind of like extra light gets blocked by the planet plus its atmosphere.
I think we need to revisit that
Sure.
because this is, to me, the miracle of astrophysics. This is so mind-blowing. So I'm just picturing myself, night sky, looking up at the night sky. I see these teeny weeny spots, dots of light up there, usually stars. Not usually, most always stars. So, and then what you would do is you would look very closely at one of these dots and wait for the light to slightly dim.
Yes.
And once that light slightly dims, you would say, hey, that could be an exoplanet. Is that about right?
Yes, yes.
And this is a miracle. How does that work?
And this is like, well, right. So it works because we're able to build telescopes that can look at basically large chunks of the sky at once. Yeah. So we're very efficient. We can look at a whole bunch of stars at once. And we have clever ways to do massive like searches of this big data and say, okay, are any of them, blinking, essentially? Like, are they blinking periodically?
I mean, like extremely faintly blinking because you've got a huge star considering our sun and the size of the Earth.
Yeah.
The Earth is nothing.
We're looking, so we say we're looking for blinking, but it's at the level of sometimes like 0.1% of a change in the brightness. So very tiny measurements, not even 1% of a change, right? Like 0.1%. And so imagine that, we look and we can detect that, and we have. That's how we found, thousands of planets this way. So we can detect these periodic blinks and we say,
because the
planet's orbiting.
Orbits the sun. Yeah. That's where
exactly.
the periodicity comes from.
It'll orbit, some planets take hours to orbit around their star, which is also mind-blowing because we take 300
planet.
Yeah, we take 365 days to orbit around our star. Some of these planets take hours or days or tens of days. Like we found the whole range so far, and we're finding longer and longer orbits, the further we look, because it takes time to find a planet that, takes years to orbit around its star. So we're still looking. But yeah, exactly. We can say, okay, this star is blinking every 2 days, and let's see, is the shape of the blink, like we can measure that and see how the star looks when it dims. We're just measuring how brightness changes over time, and it has a certain shape to it. And we say, okay, that shape actually tells us it's a planet, or at least something that could be a planet. Sometimes it's another star, because stars do orbit other stars.
Binary stars.
Yeah. So that's something that can trick us a little bit. But for the most part, it's another planet, or a planet, not a star, orbiting another star.
And you would then analyze the light from that star.
Yes.
And by blocking parts of the star, you could then deduce the composition of whatever is passing the sun or the star.
Yeah. So imagine again, so the whole planet will block, 0.1% of light from the star. But then the planet, we're assuming most planets have atmospheres, which is a fair assumption, because most of the ones in the solar system do. But so imagine now within that 0.1% of light that's changed, that we've measured, we're looking for like an additional, 0.1% of another change. So it's like 0.1% of 0.1%. So it's extremely tiny because the atmosphere is relatively small compared to like the core of the planet, the whole planet itself. I mean, if you've seen pictures of Earth's atmosphere, right, and it's beautiful, the ones taken from space, you see that Earth itself is giant compared to the layers of the atmosphere.
They say like the peel of an apple.
Exactly. So it's very small. And that's the region that we're looking for when we say, okay, that region, that peel of the apple, some of that will contain water, carbon dioxide, methane, and those molecules will block some starlight at that 0.1% level. And
We're all-
we can measure that.
You're superheroes.
Yeah, we can measure that. And we found water in a ton of planet atmospheres already. We found carbon dioxide. We found sulfur dioxide. We found methane. The list goes on. And it's incredible. And it's only the beginning because now the James Webb Space Telescope basically works so incredibly well. It was not really designed for this because the inception for the telescope kind of started before we knew of that many exoplanets. But it was now designed, or, it's been enhanced, if you will, to make sure that we could study exoplanets with the telescope. And it's working phenomenally well. We've been able to already make the first actually definitive detection of carbon dioxide outside the solar system in an exoplanet atmosphere.
CO2.
Yeah.
What does that mean?
Well,
Signs for life?
Well, it's not a direct sign for life, but it's also like with water. I mentioned methane. These molecules, they all have carbon, hydrogen, and oxygen, these key elements that are effectively the building blocks of life. They're not direct signs that, an atmosphere is hospitable. Like if we find water in an atmosphere, it doesn't mean there's a liquid ocean on the surface. There could be, but
Could be water vapor.
yeah, it could just be water vapor in the atmosphere. And so, but all these together, the carbon, oxygen, and hydrogen, these are key elements. Like we're carbon-based life forms. We know there's certain elements that came together to bring us where we are today, right? And so every time we measure one of these molecules, we are able to say how much, carbon, oxygen, hydrogen is in that planet, to begin with. How much might have come from other sources? Like, did the planet originate with all that in its atmosphere? Did it evolve over time? Could it be evolving now to something more hospitable? So you kind of get a starting point of, okay, what's the content? What's the quantity of all these molecules and elements? And what does that really mean for the likelihood that they could come together one day, to, again, form a habitable type environment?
Does life need to be carbon-based?
Well, probably not, but it's the only thing we know. So it's sometimes, it's hard to do a blank search, right? So it's like you have to start somewhere. So that's why a big goal is, studying Earth-sized planets around stars like the sun to try to see if we can find an Earth twin, because it's the only thing we know for sure that can sustain life, right?
Is there a recent discovery that keeps you awake, or a most promising discovery when it comes to exoplanets where you think like, wow, we're onto something maybe? Or is it too early still because you're still digging through James Webb data?
Yeah, I mean, there's a lot of interesting things that are coming up. I think it's too early to tell with James Webb data because it's still so new. But also, I know with every observation, we're bound to make a new discovery as well. At least maybe not always discovering new planets, but at least saying, oh, in this planet, we'd never seen this before. We'd never seen that before, right? So we're going to be able to get statistics that go beyond saying, okay, we know of over 5,000 planets, but now look at all these planets that we know what they're made of. And then we can start to get like population studies and say, well, how many have carbon molecules, or how many have water at this, abundance level, or what does that mean statistically speaking? Like, how can we extrapolate, right? So that's really neat to think about. But one thing that fascinates me that I hope the James Webb Space Telescope will help us understand is how many planets have we, measured their sizes and masses and their basic properties, but how many of them might actually have ring systems or moons? Because we, again, see in our solar system, Jupiter, Saturn, all these planets have giant rings and moons, And the moons could be habitable or hospitable. Yeah.
But that's the 0.1.
Yeah, exactly.
Situation.
Such a tiny, tiny percent. But if we can start by saying, okay, which of these planets could have rings or moons, if we can get to that level, that would be fascinating, I think, to open new doors. It's not just about finding Earth twins, but it's about all possible scenarios, again, just thinking about our solar system and Europa and Titan, right? Can we find those analogs?
What kind of telescope would we need for that?
I mean, yeah, that's a good question. Well, the James Webb Space Telescope, it's not a small telescope. It's 6.5 meters in diameter. It's very sensitive to making measurements, but it's, we probably would need something bigger or maybe sensitive at different wavelengths of light, because the James Webb Space Telescope focuses in the infrared where we can't see, but it's like night vision goggles. We're seeing thermal emission and heat from the universe when we look at those wavelengths. But we might need visible light where we can instead measure reflection properties from bright moons orbiting around giant planets or something. That might be a better way to go about it. But they're already in the works. I mean, NASA actually has missions in development after the James Webb Space Telescope already. And one of them coming down the line that we're starting to think about what technology we need is actually called the Habitable Worlds Observatory.
Huh.
So that's a new concept, if you will, that we are now starting to dive into. It's not being built or anything because we need to understand the technology, right? How big does the telescope need to be to detect a habitable world? And in this case, it is focused on Earth-like planets around sun-like stars. But that doesn't mean it wouldn't be sensitive then to other scenarios like moons around giant planets. And that would certainly be bigger than the James Webb Space Telescope, or if not bigger, at least the same size. And very sensitive to complement the James Webb Telescope and probably optical wavelengths, visible light. So all these things are in the works already because that's where we're headed. Yeah.
I spoke with Lisa Kalteneck at some point, and she said, if there is life out there, we will know within the next 15 years. I know it's a bold prediction, but the hardware and the engineering and the bits and pieces of scientific tools we have in order to say if there's something out there or not. How do you feel about it?
I mean, it's a fascinating question. I would love, I think my opinion is that I would love to say that we found evidence of life in my lifetime, whether that's 15 years or, I'm middle-aged too, I guess. I don't know. So I have, in my lifetime is not unreasonable. In the next few decades, we'll say. So I feel like it's really promising to say that. I feel good about saying that. But I guess I'm not counting on it is my point. I don't know. It's funny because I'm an optimist and
you don't want to be frustrated.
Yeah. I mean, I want to be proven wrong, I guess. I guess I'm not expecting life to be found or evidence of life to be found in my lifetime, but I would love to see that happen. But it's hard because everything we do is really hard. We talk about these percentage of a percent, to signals that we're looking for. And that's in some cases just to detect that there's an atmosphere at all on some of these planets. So, how do we detect life? I do think we need different innovative ways to look at other things, like technosignatures, like evidence of technologically advanced civilizations that people have thought about, with radio observations. Can they detect radio signals from other civilizations or any other evidence of technical capabilities that we could detect.
Sometimes we get strange periodic radio pulses, and then everyone's ears are like very attentive. But usually that's a different source, I guess.
Yeah, the universe is an interesting place. So it creates all kinds of signals on its own without, aliens interfering. So yeah, there's always explanations for any odd signals we get.
How about our radio signals when we started the television radio era? So are they still out there? Like onion peels?
Yeah, they are.
At the speed of light?
They are. And, it's true, as anybody could pick them up if they have the right frequency, right?
Really?
They just need to dial in. I mean, the message might be garbled, but they would still detect something because it's still all these waves, all these, sounds that we're making now, like every wavelength, it doesn't just die, it's kind of out there in the universe. That's why we are able to detect light from these planets and galaxies and all that's traveled hundreds, if not billions of years to get to our telescopes. You just need sensitive enough telescopes to detect these things because they're much weaker signals, essentially. The radio and all that.
Would it be technically possible, provided one has the proper equipment, to listen to a newscast from 1923 out there?
Yeah.
Or watch the news from whenever, 100 years ago?
I think with the right capabilities, if you have, exactly, the right technology, signal strength of your receiver and the right frequency, so you could tune in.
In a live show, that is. And that's the interesting thing, because if you're at the forefront of that radio wave, it's live, because this is the moment when it was broadcast.
Yeah.
That's interesting. So it doesn't dilute the radio signals. Are they as strong as they are on Earth?
Well,
from those transmissions,
right? I mean, it's kind of like, sometimes you're in your car, right, and you're driving away from your hometown, and you listen to your favorite radio station at home, but then over time it starts crackling,
exactly.
right? Like
this is what will happen.
Losing the signal, yeah. But if you were pointed in the right direction towards, where the signal originated from, and you had a sensitive enough receiver, you optimized, like amped up all your tunings and all that. I mean, the radio waves are broadcast in every direction, like physically, if you will. So sometimes you just need that direct connection to get that. If you're driving in your car, you're losing that direct connection, right? But if you were, in the right spot with the right receiver,
great.
You could hear it.
How is working with James Webb or Hubble or whatever telescope? What is that like? Do you get to direct the telescope's attention to the point of your interest? Because you're saying, hey, I feel like there may be a planet. Is there a huge rivalry amongst scientists for telescope time?
I mean, I don't know, rivalry is the word, but it's definitely competition. Yeah. It really is. I mean, there's only so many hours in a day, right? And these telescopes are observing continuously.
24/7.
Yeah, so 24/7, no pause. And so, we want to make the most of them. But even with that, there are thousands of astronomers in the world who request time. They request hours on these telescopes. And not everybody can be approved for time because there's only so many hours in the day. And what they do is they plan, they being NASA and the Space Telescope Science Institute actually is located in Baltimore, Maryland. They run like the operations. So they do all the scheduling for the telescopes and all that. And they will,
So there's a Google Calendar out there?
yeah, yeah, they will schedule everything. Exactly. Like, typically on a weekly basis, they jam pack the schedule. They fill every hour that they can, but there's only so many hours a day. So they can't schedule everything, but what they do is they plan basically in yearly cycles. So every year, astronomers, and I mean anyone technically can propose to these telescopes, but astronomers will put in a proposal and say, I want to observe this target for this many hours with this camera, in this wavelength and all these settings. And sometimes it gets approved, sometimes it gets denied. So if it's denied, then you have to try again next year, And yeah, they build a schedule from what does get approved, and that becomes, the schedule for the year. Although there's always new things that can come up, like, we talk about the universe, things go bump in the night all the time. So sometimes there's like a supernova, let's say, goes off where a star will explode as it's dying. And that's really exciting to study the end stages. So we might interrupt the normal schedule to go catch what the supernova has done before it fades away and we can't detect it anymore. And so there are things that kind of interrupt the normal schedule. But otherwise, we try to stick to, this is what's approved, this is what we need to observe when it's observed. It's a big puzzle to fit everything in, to observe as many things as you can in a year. But it's a cool puzzle to solve, I think.
Fascinating. You keep reminding me of that beautiful movie Contact from the 90s, I think it was.
Yes.
Do you like it?
I love it. Yeah.
Do you identify with the main character?
I do, yeah. And
that telescope in Puerto Rico, I think it fell apart, right?
it did.
How does that feel to you?
Oh, that was a sad day because that telescope effectively started my career in astronomy, because when I was in college, I actually did a summer internship there.
No.
At Arecibo. And I was like, I am like the character in Contact, I am here.
You were the Jodie Foster.
Yeah, I was here using a radio telescope. Wow. I wasn't looking for aliens like she was, but I was studying a region where stars were forming, and you can detect some of the molecules in the cloud. Yeah, it was really cool.
Was the Arecibo telescope the James Webb of its time?
I think that's a fair statement. I mean, there's a lot of radio telescopes all over the Earth, but that one is absolutely revolutionary. I mean, it was a single dish, a giant dish, like over 300 meters in diameter. Is incredible. They literally built it in the ground, like it, because it was so huge. And it was like a giant bowl in the ground, but it was so powerful.
Who built that? Was it a NASA project?
It was working really with the National Science Foundation. Yeah. So, because NASA mostly does space-based astronomy, and then in the U.S., the National Science Foundation handles a lot of the ground-based astronomy. And then sometimes they have joint programs. They work together because really you need ground and space to work together to learn everything. But yeah, there's these kind of the two major organizations are NASA and then the NSF. And so it was decided after, the catastrophic event. I think it was from a hurricane that passed through Puerto Rico that, took out the telescope, and it got damaged enough that it was decided, the NSF decided not to repair it.
You can't repair it.
Yeah. And so that was a sad day. Because that's where my astronomy journey really started when I was in college. Yeah. So it meant a lot, and not just because of the movie Contact too, but it was, just my own personal history there.
So that means you're not just a scientist. Are you a space nerd?
Yeah. I mean, I think so. I love science fiction and fantasy movies and books, and every time I'm outside, I'm always looking up. That's just what I do. I'm like, oh, where's the moon at tonight? How's it look?
Do you use those fancy apps on your smartphone, the night sky apps? That's pretty useful.
Those are super useful, yeah, because I admit the irony is, even though a space nerd, astronomer, trained, right, I'm really bad at pointing out where things are in the sky.
Not good.
Yeah, because honestly, most of my time is spent using a computer because everything's automated or
looking at numbers.
Yeah, like I don't, even log in and point in the James Webb Space Telescope. I just tell someone where I want to look and when, and then they do it. So I don't have to know where the star is tonight, right? So it's it's funny. So my dad will often ask me, if I'm home visiting, like, oh, what's that? I'm like, I don't know.
Let me check.
Let me get my app.
Yeah. What's your favorite star or your favorite place up there?
My favorite, I would pick a constellation. Mm-hmm. Yeah, so Orion. So Orion's a hunter, but it's really iconic because there's Orion's belt. It's 3 stars in a row, and then there's like 4 bright stars that make up, the shoulders and legs, essentially, or maybe it's his knees, but still, you could tell it's like a form, humanoid shape, I guess. And I think I mean, it's recognizable in the sky, so that's one reason it's a favorite, sure. But I moved around a lot when I was younger and like in college and after college and grad school and after grad school. So sometimes the stars are constant in all the moves. And so it was nice to always be able to look up and see something recognizable, even if you're in a new, city or state or something, right? And so Orion was that for me, that recognizable constant.
That's an anchor.
Yeah, an anchor, exactly.
That's home.
Yes. Yeah.
Beautiful.
Yeah.
Would you ever consider traveling yourself to the stars? Because we're all in the middle of becoming an interplanetary species.
Right.
Or do you prefer the telescope?
I think today I prefer the telescope. If it were like, taking a plane from Maryland to Austin, Texas, then sure, I will travel in space. But yeah, I think it would be a while. I don't have a need to be one of the first explorers, of another world. I'm happy to do that with my telescope, here on Earth, because there's so much to learn and support those who can venture forward or, choose to venture forward and go to Mars one day, maybe, right? Go back to the moon. That's something else that, NASA's planning with its Artemis missions is sending the first humans to Mars. And I am all for it, but I will be gladly watching from home. Yeah. And I'm okay with that. I mean, I have a certain level of adventure inside me, but I'm also happy to live vicariously through other people.
Completely understandable, especially in a situation right now where there's no return ticket, maybe.
Yeah, I think
it's kind of tricky.
Yeah. It's
especially considering that it's not really possible to have a Earth-like life on Mars.
Right.
Opening windows.
Yeah, it's not like catching the Martian breeze is a thing that you can do. Yeah. So I'm happy, to stay here. But then there are folks like, my brother has, I don't know, maybe half joked, half not joked that he would love to go to Mars and be on the forefront. And he's a pilot, so he could be a good fit for that type of project, to go explore. He's traveling all over the world all the time. So that's his personality, and he loves adventure like that. And so I'm like, I would fully support if he wanted to go, Do
you have a take, maybe that's a little philosophical, but do you have a take on what is going on Earth right now when it comes to this new leap forward in the space industry, new space and everything that's going on? It feels like that humanity is growing wings to leave Earth. Is that too philosophical? How do you feel about it?
Yeah, there's some truth there. With the different companies, SpaceX or Blue Origins, right? And on all these companies that are
Virgin.
Yeah, looking to kind of whether it's like, leaving Earth just to do it, right? Just to say you've done it, or whether it's, leaving Earth for another reason or just to be the first. I think these are all questions like, what's the motivation? Like, why really are so many companies interested in this? I think that's unclear. Like, at least for NASA, it is about the science of exploration. We want to be able to go to the moon and Mars, to have astronauts there to do science. We're not just exploring, for the sake of exploring. But it is also to prove that we can do it. That's a big part of it too. Like, we need to push to the next steps, and then while we're there, take advantage and do science, right? And learn from these other planets and moons. But at some level, it is about doing the hard things, just to prove that you can do it. So then you can do the next hard thing, like, maybe sending a human to Europa or Titan, and then, okay, what about the closest exoplanet, right? And how do we get there? So every step enables new technology, which is really exciting. But I do wonder, I don't know if there's that inherent need now, like of folks saying, well, we've kind of explored everything on Earth. So is it?
We ran out of continents.
Is it time to move on to other areas? And what does that mean for, if who knows what country or, company lands on Mars first? What does that mean? Like, do they stake a claim to Mars? Do they colonize Mars? I don't know. Right? Is this going to be a really bad science fiction movie? Or is it just an exciting era, that brings humanity together? I think it remains to be seen, right? Like, what will happen when the day comes? Because I do think it'll come, where we land the first humans on Mars. Like, how will that be for humanity? Because we've already been to the moon and we want to go back, and that's exciting. But going to Mars is something brand new, right, for humans.
And how would we govern Mars? I think I may be mistaken, but I think a couple of years ago, Elon Musk said that not necessarily our governance systems and the way we do things on Earth apply to Mars. So if he sets up something on Mars, maybe it's a different kind of governance. That sounds intriguing, but at the same time menacing.
Exactly. So I think it's a huge question, right? Of does somebody have to get there first? Does it have to be NASA? So it's a purely scientific effort, and if it's not NASA, then what does that mean?
Yeah.
Right.
What kind of body is that? Is in terms of governance?
Right. And it's interesting because even with the International Space Station, we partner with these companies already. SpaceX is launching NASA astronauts to the International Space Station already. And so we are working together. And I think that's an important thing to do, is really keep working together, right? To keep these relationships open so that it's not a competition, but it's a human, activity, right? It's a human race activity, a singular human race. It's not who's first, and who wins the race. It's a joint collaborative effort.
Yes.
Yeah.
Knicole, for the long haul to the stars, provided you're going at some point, it's gonna be a very boring and very long ride. You will bring your Spotify playlist. Which tune would you want to bring on that playlist? By the way, we set up a real playlist for just that.
Okay.
And now it's your time to introduce your favorite tune to that list.
Oh my gosh. Probably Imagine Dragons, Radioactive, perhaps, because there's a lyric in there that says, "I'm waking up." And so, starting off with Imagine Dragons and saying, here we are, on this incredible journey, just driving you. Yeah. So they're one of my favorite artists. So I'd be happy to listen to them the whole way to whatever exoplanet we're going to.
Trappist.
Yeah, Trappist probably, for sure.
This show is called the Space Cafe podcast. It's a coffee place. And in coffee places, now and then you have an espresso to energize yourself. Why don't you share an espresso for the mind with us now to inspire, even more inspire me, the audiences. And the topic is completely up to you.
Okay, so what gives you that caffeine jolt?
Yes, for the mind.
Yes, for the mind. Well, I think, it boils back down to if you ever feel like you're alone out there, right? Just think there's no way you can be. There's billions and billions of planets. There's got to be more out there. So really, you're not alone, even if you think you're alone, you're not. There's so much out there in the universe waiting to be explored. So just try to fathom that. And that's a lot to take in the morning. But, it's a way to remember you're not alone because the universe is very big, but in a good way. There's a lot to look for out there.
Wonderful. Knicole, thank you so much for taking the time.
Thank you.
And that's a wrap for today's Space Cafe podcast. Our immense gratitude goes out to Dr. Knicole Colon for her illuminating insights on exoplanets and the future of space exploration. We discovered the thrill and challenges of hunting for other worlds, the excitement of new scientific discoveries, and we pondered some deeply philosophical questions about humanity's future in space. Remember, no matter where you are, you're never alone in this vast expanse. There are billions of planets out there waiting for us to discover and perhaps one day call home. If you enjoyed our conversation today, do subscribe to the Space Cafe podcast for more mind-bending conversations about the cosmos. And don't forget to check out our Spotify playlist, where you can find the tunes our guests would take on their journey to the stars. I'm Marcus. I'm signing off from the Space Cafe podcast for today. As always, keep looking up and stay curious, my friends. Until next time, bye-bye.